The problem statement from GATE Physics 2014 reads as follows. The minimum number of flip-flops required to construct a mod 75 counter is. This is a numerical answer type question, and once we find the answer, we'll try to fill in the blank here. When solving any type of problems relating to counters, we need to talk about their building block, which is the JK flip-flop. So on the left you can see the symbol for this flip-flop. So this is the symbol. J and K are the inputs and Q and Q bar are the outputs, and a clock, and this J flip-flop runs on a clock. This is the clock, and in this case this flip-flop is running on an edge triggered. You see this triangle, this denotes an edge, and it's a negative edge triggered. So for instance, let's say if the clock is something like this, then the output, this truth table will come into effect only when at the negative clock edge. So you see this is being denoted by this downward symbol here, that only at the negative clock edge we'll evaluate the values of J and K and accordingly update the value of Q if needed. So for instance, let's say we are on the negative clock edge and J and K are 0, then the next value Qn plus 1 is the same as Qn. It does not change. So we say is retained. On the other hand, if at the negative clock edge J is 0 and K is 1, the next value of Q is 0. This is often known as the reset condition. Similarly, if J is 1, K is 0, the value of Q is set to 1. This is known as set condition. And finally, if J and K both are 1 at the negative clock edge, then the next output of this flip-flop, this Q, is nothing but Qn bar. This means this is known as the toggle, because if the next output is nothing but the inversion of the previous output. Now we use these flip-flops and these 4 flip-flops to create a circuit. We have used 4 flip-flops. This is a 4-bit ripple counter. This is the ripple counter circuit, and the Q0 is the least significant bit and Q3 is the most significant bit. It's again it's to emphasize that the output of first flip-flop is the clock of second flip-flop, which you can see in all the 3 cases here. And J and K are set to high. So this means this JK flip-flops are operating in the toggle mode, and this is also referred to sometimes as a mod 16 counter. Why mod 16 counter? Because this counter will count from 0, 1, 2 and up to 15, and then again it will be 0. So that's why. And why mod 16? Mod stands for modulo. So when you take the remainder of 16, it will come anything between 0 to 15, hence the name mod 16 counter. In general, if there are n bits in a counter circuit, there'll be n flip-flops. So because each flip-flop contributes 1 bit, and it will be a mod to 2 raised to the n counter. So let's say if there were 3 flip-flops, so this means the maximum value it can be from 0 to 7. This means modulo 8. So mod 2 to the power 3 is modulo 8, right? And so on. So this is just a good thing to remember. Okay, so now that we have seen that how JK flip-flops is being required to construct counters, and we also saw the definition, we also saw this expression that n bits is equal to n flip-flops, and it is equal to mod 2 to the power n counter, right? So let's just assume that, let's say this is that we need to find the minimum number of bits. So let's start with a small number. Let's say n equal to 2. So if n equal to 2, then it will be a 2 to the power 2 mod 2 to the power 2 counter. This means this will be a mod 4 counter. Clearly this will not count, so we need to count to 0, 1, 2 up to 74. This counter will only count to 0 to 3, so this will not serve the purpose. So let's increase the number. Let's say n equal to 4 now. This will be mod 2 to the power 4 counter. This will mod 2 to the power 4 is 16, so this will be mod 16, and again this will count to 0 to 15. Again this will not work, we need to go to 74. So let's now try n equal to 6. So this will be 2 to the power 6, mod 2 to the power 6. So mod 2 to the power 6 is mod 64 counter. This will count from 0 to 63. We are close, but we are not there yet. We need to go to 74. So this means we need to go n equal to 7. This means it will be mod 2 to the power 7. This will make it mod 128 counter, and now we can count from 0 to 63, 64, and then somewhere will be 74, and finally it will be 127. Now we can, using this n equal to 7, this means 7 flip-flops, we can go up to 127, but using the circuits we can stop even at 74. So but we must go to at least 74, which you cannot go with 6 flip-flops, so we need at least 7 flip-flops. You can use 8, and then again you will have to stop at 74. So the correct answer here would be that in order to implement a mod 75 counter, which means we must go till 74, we need at least 7 bits. So the answer here would be 7. 7 is the correct answer. Thank you for listening.